We're looking at section 3.3, complex numbers. These are the topics we're going to cover in this lecture. Up until now, we said you cannot take the square root of a negative number. We're now going to make this possible through notation. We're going to define I to be equal to the square root of negative 1. Therefore, if we square both of these sides, we get I squared is negative 1. So now we can actually reduce expression. If I take the square root of negative a, this is equal to I square root of a, assuming a is a positive number. Negative a would be negative, and the square root of a negative 1 is simply I. Let's look at simplifying the following expressions. The square root of negative 36. I have the negative inside the square root, so I can actually pull that out, and the square root of negative 36 becomes I square root of 36. And we know that the square root of 36 is simply 6. So this becomes 6 times I, which is 6I. I have an answer, negative 2 plus or minus the square root of negative 8 all over 2. Again, I have the negative inside my radical. So the square root of negative 8 simply becomes I square root of 8. So negative 2 plus or minus I root 8 over 2. I need to reduce the 8. The 8 is 4 times 2. 4 is a perfect square, which I can pull out, and the square root of 4 is 2. So I square root of 8 becomes 2I root 2. And notice this 2 out front, this 2 in front of the radical, and this 2 in the denominator are all divisible by 2. So negative 2 divided by 2 is negative 1. 2I divided by 2 is I. And I'm left with the root 2. So this is negative 1 plus or minus I root 2 would be my answer. Now we need to extend this to other calculations, not just simplifying expressions, but let's actually perform operations on these. Whenever we multiply numbers with negatives in the square root, we have to pull the I out first before multiplying the radicals with negative numbers in them. So if I have the square root of negative 3 times the square root of negative 27, this becomes I root 3, I pull the I out first, times I root 27. I times I is I squared. Square root of 3 times square root of 27 is the square root of 81. I squared by definition is negative 1. So this is negative 1. Square root of 81 is 9. This gives us negative 9. Similarly, the square root of negative 5 times the square root of negative 5 is I root 5 times I root 5, which is I squared times the square root of 25. I squared is negative 1. And root 25 is simply 5. So this becomes negative 5. If we were not to pull the i's out first, we'd actually wind up with positive numbers, which are incorrect. So we have to deal with the i's at the very beginning. There's something called the standard form of a complex number. A complex number can be written in standard form with its real part and its imaginary parts using the expression a plus bi. A is the real part. It's just a real number. I is called the imaginary part because of the I in there being an imaginary number. Let's look at operations with these. Write the following the following expressions in standard form. We're going to follow the basic order of operation. We can only add and subtract like terms. However, we can multiply and divide unlike terms. So if we have negative 4 plus 2i minus 6 plus 5i, what I'm going to do is drop my parentheses on my first one. So negative 4 plus 2i minus 6 minus 5i by distributing the negative sign into each one of these. Now I'm going to group. My real terms, the negative 4 plus the 6. And then I'm going to group my imaginary terms, the 2i minus 5i. So negative 4 plus 6 is 2. 2i minus 5i is negative 3i. I can also do multiplication. When we go to multiply 5 minus 2i squared, this is 5 minus 2i times 5 minus 2i. This is foiling. We get 25 minus 10i minus 10i plus 4i squared. This I squared is usually what throws people off. Because why? The 25 stays the same. The minus 10i becomes minus 20i. The I squared is negative 1. So 4 times negative 1 is negative 4. And 25 minus 4 is 21 minus 20i. The division is usually the hardest one of these. The reason we have to divide is that I is a radical, and by the standard rules of math, we cannot have a radical in our denominator. What we're going to use is what's called a complex conjugate. Complex conjugates are a plus bi and a minus bi. And we'll apply complex conjugates to get rid of the radical in the denominator, get rid of the I in the denominator. So I'm going to start off with 4 plus 5i over 2 minus 3i. What I'm going to do is just focus on the denominator. And 2 minus 3i has a conjugate of 2 plus 3i. So I'm going to multiply the numerator and the denominator by 2 plus 3i. The reason I'm going to do that is I can multiply anything by 1 and not change its value. So 2 plus 3i over 2 plus 3i is just 1. And I want the conjugate of the denominator because I want to get rid of the I in the denominator. Let's see how the denominator works first. We're just going to FOIL down here. 2 times 2 is 4. 2 times 3i is 6i. Negative 3i times 2 is negative 6i. And negative 3i times positive 3i is negative 9i squared. Similarly, we're going to FOIL in the numerator. 4 times 2 is 8. 4 times 3i is 12i. 5i times 2 is 10i. And 5i times 3i is 15i squared. The I squareds are the kickers now, okay? Remember the I squareds equal negative 1. In your numerator, you're going to combine the 12i and the 10i and get 22i. In the denominator, you're going to get 6i minus 6i is 0i. So notice, at this point in time, there's no i's in your denominator. You simply have 4 minus 9 times negative 1. So this gives us, I can actually get rid of this step here. I'm going to do it because it's redundant. The 8 minus 15 is negative 7 plus 22i in the numerator. And the 4 minus 9 times negative 1 is 4 plus 9, which is 13. I now have a complex number with no I in my denominator, which is really what we want. Alright, solve the following quadratic equation. We have x squared plus 2x plus 5 equals 0. If we plug into our quadratic formula, we get x is negative b plus or minus the square root of b squared minus 4ac all over 2a. This gives us x is negative 2 plus or minus, this is 2 squared minus 4 times 1 times 5 all over 2. This now gives us 2 plus or minus the square root of negative 16. We know negative 16, the negative becomes an I, square root of 16 is 4. So negative 2 plus or minus 4i over 2 is negative 1 plus or minus 2i. Now, how do we graph these? Well, we can't graph these on the regular xy coordinate system. But it doesn't really matter because if I look at the graph of y equals x squared plus 2x plus 5, notice it does not cross the x-axis. Okay? And again, there are no real solutions, which correspond to this, because if it actually crossed the x-axis anywhere, if it crossed it once, we'd have one real solution. If it crossed it twice, we'd have no real solutions. If it doesn't cross it at all, if it crossed it twice, we have 2 real solutions. Crossed it once, 1 real solution. If it doesn't cross it at all, we have no real solutions. And this is what we have here, no real solutions. So the 2 complex solutions confirm that this graph does not cross the x-axis.